I'm Rita.
I'm Finn.
And for the next 4 days, we are going to work with blue mussels here in Texel.
As we all know, the problem of sea level rise has become an increasing concern all over the world. It affects sedimentation rates, usually meaning a lower sedimentation rate. The blue mussel, Mytilus edulis, is an active suspension feeder, subsisting mostly on algae and detritus. The Wadden Sea is an important region for mussel farming in Europe, and so the destruction of extant marine habitats can increase the concentration of suspended solids in the water, becoming a problem for blue mussels. Turbidity in water ranges from 0.04 to 0.56 grams per liter. This information allows to determine filtration rates and more, and consequently have a better understanding of factors that affect it. In similar mussel species, large amounts of suspended solids can interfere with the feeding process. However, there is a knowledge gap concerning this, as there is very little research on Mytilus edulis responses to changing sedimentation rates. So, our research aim is to assess the effect of different sedimentation rates on filtration capacity of blue mussels in the Wadden Sea. And to do this, we are going to work with our primary research question. What is the effect of increasing sedimentation rates on filtration capacity of blue mussels? To answer this question, we need to know what rate of sedimentation acts as a turning point for the filtration capacity. Finally, our research hypothesis is it is expected that the filtration capacity of mussels will increase with increasing values of sedimentation rates.
Louise, I am so confused. How are we going to do an experimental setup to try and respond to all of these questions?
Well, Rita, we want to test the effect of different sedimentation values. So we're going to have 3 sedimentation values that we're going to test. One is going to be lower sedimentation rate than in the sea, one that's about similar, and one that's much higher. We are going to gather a bunch of mussels that are similar in size. We want them 3 to 4 centimeters big. We're going to measure them and then we're going to weigh them. Now it's time to set up some tanks. We're going to set up 15 tanks in total, 3 with different sedimentation values and 2 controls. We're going to fill all tanks with 2 liters of seawater. In the control tanks and in one experimental tank, we're going to add the locally sourced sediment. To all tanks except for the one, we're going to add the algae for the mussels to eat. The first control will not have algae, so we can observe the filtration of the mussels in absence of food. Now it is time to add the mussels. We're gonna add 5 mussels per tank, except in the second control. We leave that empty. Now that all tanks are set up, it is time to start our measurements. We also took some water samples to assess the current amount of sediment that the mussels live in the wild. We have 2 locations that we took the samples from, the south of Texel in the Wadden Sea, and on the west of Texel in the North Sea. We're going to use this information to relate our findings of our experiment to the current sedimentation rates in the seas. Well, Finn, I'm going to give the word to you. You can tell our viewers about our results.
Thanks, Louise. Now I'm here to talk about the results. Once we got back to Wageningen, we received and weighed all of our water samples to test natural suspended sediment levels in the North and Wadden Sea. We found that while the Wadden Sea is quite stable at 0.08 grams per liter, the North Sea differs quite a lot between incoming and outgoing water, with incoming being at 0.13 and outgoing being at 0.08. We also calculated the clearance rate per tank, which we could use to calculate the clearance rate per mussel by simply dividing the total value by 5. After we'd gathered all of our data, we could then start the statistical analysis. Here we found that the clearance rate per mussel per tank wasn't normally distributed, but a QQ plot proved that the square of the clearance rate was. We filtered out control tank 1 because it contained no algae and can therefore not be directly compared to our other treatments. After doing a one-way ANOVA test, we found that there were no significant differences between treatments. This is a somewhat surprising result, as this requires us to discard our initial hypothesis.
Thank you, Finn. As we can see, we have a lot to discuss. In control tank 1, we observed the highest clearance rate, likely due to the water being the clearest, minimizing any hindrance during filtration. Control tank 2 had a low, but non-zero, clearance rate, which suggests some fluctuations in the measurement even without biological activity. One limitation was the low number of sediment levels tested in the short duration of the experiment, which may explain the lack of significant results. Testing over a wider range and longer time could improve this. The values we used were validated by water samples taken from the North Sea and the Wadden Sea. However, sediment levels in the tanks could only be confirmed afterwards, adding some uncertainty. There was also a power outage during the experiment, which altered oxygen and sediment saturation, likely influencing the results. And lastly, pseudophysis increased water turbidity, which likely interfered with our measurements. But what can we conclude with this? We hypothesized that filtration capacity would increase with higher sedimentation rates, but we were not able to confirm this. The blue mussels showed no significant difference in filtration capacity across the tested treatments, meaning no turning point was observed. This suggests that within the range of sedimentation rates we tested, blue mussels are able to adapt, implying they could cope with changes caused by the sea level rise. Thank you so much for watching. See ya!
Bye bye!